Public key encryption was amazing enough, but digital signatures are even more splendid and way more important. Digital signatures provide a level of authentication for messages similar to MACs, and in modern business, authentication is far more important than secrecy. Just like public key encryption, digital signatures use a pair of keys, the public key and the private key. You still can't derive one key from the other, but this time we're going to reverse them. Alice has a plaintext message. Using her private key, she encrypts that message. Because her private key is only hers, only Alice's key can encrypt the message in precisely this way. Thus, the encrypted message becomes Alice's signature on the message. Alice's public key is public. Anyone can get Alice's public key and decrypt the message, thereby verifying that Alice indeed signed it. The signature is a function of the message, so it is unique to the message. A malicious forger can't lift Alice's signature from one document and paste it onto another. And it's a function of Alice's private key, so it is unique to Alice. Of course, real systems are more complicated. Just as Alice doesn't encrypt messages with public key encryption algorithms, she encrypts a message key instead. She also doesn't sign messages directly. Instead, she takes a one-way hash of a message and then signs the hash. Again, signing the hash is a few orders of magnitude faster, and there are mathematical security problems with signing messages directly. Also, most digital signature algorithms don't actually encrypt the messages that are signed. The idea is the same, but the mathematics is different. Alice makes some calculation based on the message and her private key to generate the signature. Then, this signature is appended to the message. Bob makes another calculation based on the message, the signature, and Alice's public key to verify the signature. Eve, who doesn't know Alice's private key, can verify the signature but cannot forge the message and a valid signature. Several digital signature algorithms are commonly in use. RSA is probably the most popular one. L8.3 signatures are another you will see occasionally. And there are signature algorithms based on elliptic curve cryptography, which are similar to all the others but are more efficient in some situations. Although public key digital signature algorithms are similar to MACs, they are better in one important respect. With a MAC, Alice and Bob share a secret key that they use to authenticate messages. If Alice receives a message that she verifies, she knows it came from Bob. But she cannot convince a judge of that fact. All a judge can be convinced of is that the message came from either Bob or Alice. After all, both of them knew the MAC key. MACs can be used to convince the receiver that the message came from the sender, but it cannot be used to convince a third party. Digital signatures can be used to convince a third party, which solves the non-repudiation problem. Alice cannot send a message to Bob and then later deny ever sending it. Random numbers are the least talked about cryptographic primitive, but are no less important than the others. Almost every computer security system that uses cryptography needs random numbers. For keys, unique values in protocols, and so on. And the security of those systems is often dependent on the randomness of those random numbers. If the random number generator is insecure, the entire system breaks. Depending on who you talk to, generating random numbers from a computer is either trivial or impossible. Theoretically, it's impossible. John von Neumann, the father of computers, said, "Anyone who considers arithmetic methods of producing random digits is, of course, in a state of sin." What he means is that it is impossible to get something truly random out of a deterministic beast like a computer. This is true, but luckily we can get by anyway. What we really need out of a random number generator is not that the numbers be truly random, but that they be unpredictable and irreproducible. If we can get those two things, we can get security. On the other hand, if we mess those two things up, we get insecurity. In 1994, the Casino Montreal used a computer's random number generator for its Keno drawings. One observant gambler who spent way too much time in the casino noticed that the winning numbers were the same every day. He successfully picked 3 successive jackpots and won $600,000. After much wringing of hands, gnashing of teeth, and investigations, the casino paid up. Several broad classes of random number generators are out there. Some random number generators make use of physical processes that seem pretty random. The NSA likes to use electrically noisy diodes in its hardware circuits to create random numbers. Other possibilities are radiation counters and radio noise receivers. One system on the internet uses a digital camera focused on lamps. Other systems use the air turbulence in disk drives or the seemingly random arrival time of successive network packets. Some random number generators use random movements from the user. A program might ask the user to type a large string of random characters on the keyboard. It might use the sequence of characters or even the timing between successive keystrokes to create random numbers. Another program might ask the user to make random mouse movements or to gargle into a microphone. Some random number generators use these inputs directly. Others use them as seeds for mathematical random number generators. This process works best when the system needs more random numbers than the input provides. Whatever the source of randomness, the generator will then generate a series of random bits. These can then be used as cryptographic keys and for whatever else the system needs. One of the easiest ways to compare cryptographic algorithms is key length. The press likes to focus on this because it's easy to describe and compare. Like most of security, the reality is more complicated. A short key is bad, but a long key is not automatically good. Let's start at the beginning. A cryptographic key is a secret value that makes a cryptographic algorithm unique for those who share the key. If Alice and Bob share a key, they can use the algorithm to communicate securely. If Eve, an eavesdropper, does not know the key, she is forced to try and break the algorithm. One obvious thing she can do is try every possible key. This is called a brute force attack. If the key is n bits long, then there are 2 to the power of n possible keys. So, if the key is 40 bits long, there are about 1 trillion possible keys. This would be impossibly boring for Eve, but computers are indefatigable. They excel at impossibly boring tasks. On the average, a computer would have to try about half the possible keys before finding the correct one, so a computer capable of trying 1 billion keys per second would average 18 minutes to find the correct 40-bit key. Brute force cracks scale linearly. Twice the computers can try twice the number of keys. But the difficulty of a brute force crack is exponential with respect to the key length. Add 1 key bit of key and a brute force crack is twice as hard. Add 2 bits and it's 4 times as hard. Add 10 bits and it's 1,000 times as hard. The nice thing about brute force attacks is that they work against any algorithm. Since the attack doesn't involve the inner workings of the mathematics, the attack doesn't care what they are. Some algorithms may be faster than others, and hence the brute force attacks might be faster. But this is more than overshadowed by the key length. It's easy to compare the key lengths of different algorithms and to figure out which ones are more vulnerable to brute force attacks. Most modern algorithms have used at least a 128-bit key until recent times. We have no idea how future advances in computing will affect things. And the real security depends on several things. How valuable your data is, how long you need to keep it secure, and so forth. The key lengths are useful for discussing symmetric algorithms and MACs. Key lengths for public key algorithms are more complicated.